Good afternoon, everyone, and welcome to this second Eurodose webinar that will be about the irradiation facility at CERN, namely the CERF and the CSBF. Before starting, I want to briefly introduce you Eurodose. Okay, so Eurodose is an association of scientists gathering people from mainly all over Europe. We are at present 73 voting members, corresponding to the same number of institutions. And the governance is up to board and the council. But the core of Eurodose is actually in 8 working groups, spanning all the interested topics in radiation delivery. You can see highlighted here the working group 11, high energy radiation fields, that I have the honor to share. And this webinar today will be focused on this, on the topic of this working group. Here is a figure that show you how is increasing in time the number of participants to the annual meetings that Eurodose organizes every year. The next one will be online for obvious reasons, and the number of participants will be expected to be much higher, more than 500 attendants. A few words now on the working group. It's devoted to high energy radiation field, but also complex field and pulse field used in medicine, research acceleration, civil aviation, and space. Among the number of people in the group is roughly 80 members, coming from mainly all over Europe, but not only. I can see from the chat that there is some bad noise, but I trust the organizer will fix it rather soon. So maybe it's not the case to speak any longer, just wait a few minutes if the organizer.
Okay, just a second. Marco, do you hear me?
Yeah.
So, I don't know if the feedback is also on my sound, but it was okay when we tested half an hour ago, so I hope it's okay now. So I can take over for the introduction maybe until this feedback.
Yes, thanks. I switch off my microphone.
Okay, I'll just go back just a short while for those who didn't hear. So Marco was trying to present Eurodose because this is one of the Eurodose webinars. So this is a European dosimetry organization. We have actually already 80 voting members at the moment. We have the board, and the important thing is, of course, that we have 8 very active working groups. And working group 11 is actually the working group which organized this webinar. So working group 11 is on the high energy radiation fields, and Marco is actually the chairperson of this working group. So we also have an annual meeting every year, and you see here the numbers of participants that have risen. If we will make, actually the next annual meeting is in 2 weeks. Of course, it will be online, but just to tell you that well, the number of participants we have already registered for our annual meeting, meaning the Winter School and the General Assembly, is already over 600. So if we add this to the chart, it will go very high because of course, it's online. But basically, the working groups, they also will have all their meetings online. As I understood, Working Group 11 will have their meeting next week. So basically, Working Group 11 is on high energy radiation field. So Marco is chair, Veronika Olsovskova is secretary, and they work on field characterization and dose assessments in various activities where high energy radiation, complex and pulse fields are used. And so they also contribute to the development of international standards and recommendations. If you want to know more about the working group, please contact Marco or Veronika or anybody else from the speakers here, and we can give you more information, and you can even join if you're interested. So you see here a list of the different tasks from the working group, and actually this webinar frames in task number 7 on the high energy reference fields. So I think that's okay for an introduction. So we can go to the first speaker. I don't know, Marco, if you can try again to take over. There's still a problem with Marco. Okay, so we go to the first speaker. And so the first presentation will be on the CERF field. The first presenter is Marco Silari. He's from CERN. He's also a member of the Eurodos Council. And because I didn't prepare to take over from Marco Caresana, I cannot give much more info on Marco Silari, except that I know him for many years. So I'm looking forward to the presentation. So Marco Silari, it's up to you. Thank you.
Thank you, Philip. Thank you, Marco. Thank you, everybody. I see in the audience some old friends. Good afternoon, Manfred, my old group leader. And I'm sure there will be others who actually know CERF already. So in this talk and in the next one, given by Fabio, we'll review the CERN EU High Energy Reference Field Facility, CERF in brief. CERF in French means beer, and because the area where we have the experimental hall, it's actually full of beers in the surrounding. Now, first I would like to give a brief introduction to the overall radiation facilities we have at CERN. There are several, and these are the ones we are not going to talk about. There are a few installed in the PS East experimental areas called IRAD Charm. The GIF++ is a strong photon source installed in the SPS experimental area, which is used in combination with the muon beam from the accelerator. In the radiation protection calibration laboratory, we have a very strong, I think a 10 terabecquerel cobalt-60 source for testing essentially radiation damage to electronics. HIRAD MAT is a facility installed also, taking beams from the SPS, which is to test radiation damage to material. Vesper is the only one using electron beams, mostly aimed at space radiation studies, and the CalLab is the calibration laboratory of the radiation protection group. I mean, if you want to have more information, you have these two publications in the bottom of the slide. But what we're going to discuss today in these 3 talks is actually what we call the workplace radiation fields. Now, especially for neutrons. Now, when we're talking about neutron fields, there are a few reference fields from thermal up to high energy. The first one is, of course, radionuclide sources and thermal filtered neutron beams, which actually are from nuclear reactors. You have a few places where you can actually do experiment with the nearly monoenergetic neutron beams. The one shown is the PTB in Braunschweig. There are a few others. And then you have what we call the stimulated workplace fields, and one of those is actually CERF. Now, you know that we want to measure in neutron field, the reliable measures are rather difficult because, well, first of all, the field is rarely rather pure, but it's always mixed with other particles, with photons for sure, or around particle accelerator, you also have, other particles. You have normally wide energy range if you're talking about particle accelerator or cosmic radiation. we have a very complex and dependent interaction with matter. Most instruments, if not all, they do not respond perfectly to all the broad energy of the radiation field, and neutron have this unpleasant property of scattering a lot, which may cause problem when you do measurements. Now, CERF is installed in the north experimental areas of CERN, served by the SPS beam. So this is the aerial view of the region of Geneva. The yellow track is the path of the LHC, which is installed underground. The ring is 27 kilometers. The bluish ring, the smaller one, is the SPS, which is 7 kilometers. And the red circle identify the Parvesen site of CERN. And in Parvesen site of CERN, which you see from the top, you have a very large experimental hole. And upstream in this hole, you have CERF. So CERF is, as I said, is a simulated workplace field for field calibration of radiation protection instrumentation used around high energy particle accelerator, and also for detector used for air-crewed dosimetry. And essentially to determine the response in high energy fields, and also to perform as a field simulation. We can actually use, for instance, an instrument meant to measure neutrons on both planes, calibrated in a similar field on Earth. And the whole concept is expressed in this sketch, which I think comes from the times of maybe Hans Schraube still. I got this slide from him many years ago, which essentially at CERN we shoot the beam from the SPS, which is normally 120 JV upon C momentum. In the past we used 120 onto a copper target, and is then filtered by 80 centimeters of concrete. And this actually is similar to the amount of atmosphere that a cosmic ray coming from space interacts with before reaching Earth, so that the field outside our shielding is similar to what you have in the atmosphere. Now, this is the Fluka Monte Carlo representation, where you will get full detail from Fabio's talk of the area. The facility was really conceived in 1987. It was actually meant as an experimental area to study the spatial distribution of hadron and neutrons, and just saw those in cascade, in the hadronic shower produced in calorimeters for energy physics. It was modified in 92 and then upgraded in the present form in 93, where the calorimeter structure was replaced by a 50 centimeter thick, 7 centimeter diameter copper target with some additional shielding around, tradition of EMASE in 97. And this is actually operated regularly by our group since those times, in fact. I lost the slides. I can't see the slides anymore. Yeah, they're back here. Now, the beam comes from, the SPS beam is actually channeled via the extraction system to a target area, which is situated about half a kilometer upstream of the actual CERF area. So the SPS beam is converted into a secondary beam, which is about 120 JeV upon C momentum with a maximum intensity of 10 to the 8 particle per SPS pulse. And after about half a kilometer traveling, it gets to this small irradiation cave. It goes across a reference ion chamber we call PIC, is an ion chamber, which is a very sophisticated device. It goes through a multi-wire proportional chamber, which is used to monitor the beam profile during radiation. And it hits a copper target. Now, this copper target can actually be installed in the position where you see it, which is below this 80 centimeter thick concrete shield, which reproduces essentially the cosmic ray field. But it can also be installed in between the PIC and the multi-wire proportional chamber. And then in that case, it sits below a 40 centimeter thick ion shield that produces a completely different spectrum. And you see the two spectrum here. So the left plot shows the dark spectrum is the one outside the concrete, which is actually dominated by a high energy component, about 100 MeV, plus of course the evaporation peak, which sits around 1 MeV, and then the continuum. Outside that the ion thick shield, you get a spectrum which is remarkably different. It is, I lost again the slides. it is actually, I don't know if you see the slide, yeah, it is actually dominated by neutrons around 1 MeV, which in the high energy peak is more. And the difference you see in the H star 10 is actually in the ambient dose equivalent. You see in the right plot. You have that outside the concrete shield, you have that most of the, about 50% of the H star 10 is due to neutron with energy above 10 MeV. So it is actually most useful to test instrumentation able to respond to high energy neutrons. Outside the ion shield, the dose mostly come, 90% of the dose mostly is due to neutrons below practically 1 MeV. Now, to monitor, when somebody exposes detectors, the reference values are given in terms of the monitor of this ion chamber, which is calibrated to give one charge every 22,000 particles per count. This calibration factor has been verified several times with the foil activation techniques. And we have as an instrument to verify the beam stability, a rank counter. It's essentially the Linus that was designed many years ago at the University of Milano and INFN, which we still use at CERF as a reference model, which actually installed in a fixed position on top of the shield, and you see the stability of the reading. If the beam is well centered on the target, the stability of the reading expresses the fact that the actual operational conditions are actually stable, and is always placed either on top of the concrete roof or the iron roof according to where we install the chamber. Now, to center the beam on the target, as I said, we have this multi-wire proportional chamber to monitor the beam profile during a run. But first of all, you have to make sure that the beam, once comes from the SPS, is actually hitting the target in the center. So for many, many years, we're actually using Polaroid films. You see in the left photo, the Polaroid film installed on a frame attached to an aluminum hollow tube, which is the same size of the target. We were actually shooting a few pulses onto the aluminum, getting in, taking the Polaroid, taking the Polaroid out, develop the Polaroid, looking at the spot. If the beam was not aligned, going back, put it back, taking out the spot, and doing on both the entrance and inner side of the target, which was a pretty time-consuming operation. You see the spot of the beam on the top right, and then in a few years we introduced a system which uses a 2 triple gem detector, which give an online imaging of the beam, so that we can actually take the shot with the upstream and downstream side of the target at the same time, and of course we see it online. We still do not have an automatic alignment system, so we still have to enter the room and realign the target manually. Now, the two photos show you a typical operation of CERF. We have 16 exposure location on top of both the concrete and iron roof shield, so we can have, in principle, up to 16 independent users working in parallel. We never have so many users at the same time, also to avoid cross interference. But typically, you have lots of detectors exposed at the same time during an experiment. There's a wide range of models that detect the CERF. More active monitor like ion chamber, rank counters, ionosphere spectrometer, TPCs, recombination chamber silicon detectors, as well as passive dosimeter film, TLDs, nuclear track detector, bubble detector. But we also use CERF for other known, say, instrumental application, like we did some spallation cross-section measurement in the beam in the past. We had quite an extensive program with colleagues from the API group on activation of accelerator material and benchmarking Monte Carlo codes, testing computer memories. In the beginning, there were some tests of the prototype beam loss model for the LHC, and we also did a shielding experiment a few years ago, in which actually Fabio was involved because he was actually his master thesis. Just the two or three slides on some example. There is a long list of papers published in CERF results. Of course, many things were done to intercompare instrumentation used for radiation protection used around energy particle accelerator. Just one example of intercomparison between different rank counters, a ionosphere spectrometer, and 2 TPCs, where you see the ratio of the instrument, the H star 10, over the Fluka reference value on both exposure fields. This was an intercomparison carried out, 6, 7, 8 years ago on multi-rank counter, where you see on the right plot the response of extended range rank counter versus the conventional rank counters and some other detector like bubble detector and TPC. We also did a few years ago an intercomparison of 4 different types of bonus pair spectrometers. The plot on the right is the comparison of the 4BSS and the Fluka using the same unfolding code. The plot on the left is the CERN BSS, the results of the CERN BSS unfolded with 3 different unfolding codes. We haven't run CERF for the past 2 years because all CERN Accelerator were at a stop because the launch shut down too. We profited to upgrade the CERF website. We had to go from Drupal 7 to Drupal 8, which required a major reformatting. And the next talk, you will have a full overview of the new reference H*10 value calculated with the latest version of Fluka, because the original were dated back to the early 90s, and the full range of particle spectra. The beam in the north area hopefully should be back sometime in summer this year. So we plan to apply for 1 week of beam time for autumn. We don't know yet the exact schedule, so we hope to get some beam time in order to provide the user with some beam time this year after a long stop. You can go to the new website where you will find at the time of the run all the information needed for the user. We are placing the complete list of the technical notes written at CERN over the years with the information on CERF. You find here a few key references that people should quote when they perform measurement at CERN. And I would like to pass on the floor now to Fabio by simply reminding, and I'm sure this list is not exhaustive, some of the people who have contributed to the operation of CERF over many years, and I'm sure some people in the audience will recognize their name in this list. Thank you very much.
Maybe just to because we had some problems with the introduction. We have decided that we will keep all the questions for the end of the 3 presentations. So we will go first to all 3 presentations, and then at the end we'll take questions. But in the meantime, please feel free to write your questions in the chat or in the question and answer, and then we can all treat them at the end. We should have some time at the end for that. So with this, I pass the word now to Fabio Pozzi, also from CERN, and he will talk about the latest updates on the CERF facility.
Okay, thank you, Philip. Good afternoon to everybody. I hope you can hear me very well. So go straight to the outline of the presentation. I will speak about the context for these latest updates and the reasons for the updates, why we needed to update something at CERF. And then I will focus on the latest Fluka simulation as already introduced by Marco, and then finally some conclusions. So the context, we at CERF, we had until 2019 a reference paper that most of you, if you are familiar with CERF, know, is the paper published in 2002 by Miterov and Marco. And it was the reference paper, as I mentioned, for almost 20 years. And it provided the neutron spectral fluence, this picture you are already seen in Marco's presentation, and provides a very detailed description of the facility with an important chapter about the muon background. It provides also the reference values for the concrete top and iron top position in terms of ambient dose equivalent. And if you read the paper, you will find this kind of table with the ambient dose equivalent in picosievert per peak count for the concrete roof shield and the iron roof shield. And then, the last point, the last part of the paper provided experimental examples of experimental application that were valid until 2002. Clearly, since then, 20 years passed, and the experimental application changed a little bit. So the reason for the update, it's mainly related to the fact that the simulated values in the former reference paper were calculated, as already said by Marco, with the quite old version of Fluka. It was the one available at the time is Fluka 92. And since then, the Fluka code has considerably improved, especially for what concerns the physics model. Then another aspect to take into account for an update is the geometry and the materials. In fact, since that time, some modification in the CERF layout were implemented, let's say maybe not really related to the CERF facility itself, but more related to the fact that some magnets were located next to the CERF roof. And these, we know that could impact the neutron scattering next to the measurement locations. And then clearly another aspects that needs to be investigated a bit more in detail are the concrete and the iron elemental composition, which can play an important role for the simulations and the reference values. Other aspects to be taken into account are that in the article from 2002, some information were not really complete or missing. An example, the particle spectra were not available in a numerical format, or if they were available, the format was not easily digestible by, for example, the unfolding codes, and the reference values for the concrete side location were missing. And then the idea was also to benchmark the new simulation with most recent measurements done at CERF, and give also an overview on most recent experimental application. And another aspects we consider was also to understand, or at least to try to investigate, the effect of the introduction of the new ICRU, ICRP quantities to these reference fields. So how we address these? We address these with 3 papers. The first one, which will be the paper, which is the paper providing the new reference values, was published last year in NIM A and cover the first 4 aspects. Then in 2017, we published a proceeding on the most recent experimental application at CERF. And finally, another paper covering especially the part related to the new ICRU, ICRP quantities, which was published last year as well on the Journal of Radiological Protection. Now I will focus more on the latest Fluka simulations, which were performed with Fluka 2011, which was the latest code version available in 2019 when I performed the simulation. The results, as already said, were documented in a dedicated peer review paper, which is available online since the 3rd of August of last year. The numerical values of these quantities are available clearly. So if you email me, I can send it to you for your calculation, but will also be soon available on the new CERF website. As already said by Marco, we are going to update it to the latest version of Drupal. And another thing we investigated in this paper was also the benchmark against the Linus. As already said by Marco, the Linus is an historical CERF reference instrument, but the choice to benchmark against the Linus is not just because it's the historical reference for CERF, but also because, as you can see from this plot, its response function follows quite well the ICRP fluence to ambient dose conversion coefficients. And additional benchmark and feedback that will come from CERF users in the future, it's very appreciated. So for what concerns the Fluka simulation, clearly everybody knowing Monte Carlo simulation knows that the 3 key aspects are the geometry, the materials, and the scorings. So for what concerns the geometry, clearly detailed geometry of the first CERF facility was implemented, including these magnets that I told you were stored next to the concrete and the iron rooftop. I put here a few pictures of the geometry with a cross-sectional view inside the radiation cave. Then for what concerns the materials, the iron elemental composition was included in its simulation from experimental measurements. So it's a realistic elemental composition for the iron layers that composed the iron roof shield. And for the concrete, since the realistic, let's say not realistic, but the experimental composition is not available, sort of standard composition was used, but also sensitivity analysis was studied to understand the effect of changing the water content in the concrete to the reference values. And for what concerned the scorings, we scored several quantities in all the reference positions. So the 16 position on the concrete top, the 8 position on the concrete side, and the 16 position on the iron top. What we scored? We scored the track length density for the several particles of interest, especially for the neutrons. We scored directly with Fluka the ambient dose equivalent, and with the offline convolution, we provided also the personal dose equivalent and the personal dose and the ambient dose, the new quantities that will be probably introduced by ICRP, ICRU. So some results that you will see here are the particle spectral fluencies for 2 positions. On the left, you have for the concrete position 7, CT7, and on the right for the iron top number 7 for different kind of particles. I would like to go straight to the comparison of these particle spectra for neutrons only for 3 positions. So in violet, you have the particle, the neutron spectral fluence at a concrete top, and in green on the concrete side, you can see that the shape is similar. Change more, what is changing is more the intensity of the 2 spectra. And in blue, you have the neutron spectral fluence for the iron top position. And clearly, we see that for the iron, we have a very well pronounced peak in the range between 100 keV and 1 MeV, whereas for iron and concrete in the region between 10 and 100 MeV, we have a similar behavior with a peak, with a broad peak centered more or less at 70 MeV. Then we compare the results of the new simulation with the former reference value. And on the left, you see the comparison for the concrete top. And the agreement is quite good between the former reference value and the new one. We are within 10% with some differences for some specific positions. And then for the iron top, the situation is a bit different because we have a systematic underestimation of the former Fluka by about 30%. It's difficult to draw any conclusion on that since the information of for the former simulation are not available. So it's difficult to say what has changed. If it is the geometry, if it is the model, if it is the chemical composition of the iron layers. Anyway, we benchmark the new results with the latest, the most recent, let's say, measurements performed with the Linus. And on the left, you have a comparison for the concrete top and concrete side. So on the x-axis, you have the reference location. CT stands for concrete top and CS for concrete sides. And on the y-axis, you have the ambient dose equivalent expressed in picosievert per IC count. In violet, the Fluka simulations, and in green, the results from the Linus. And the agreement for the concrete is within 12%, whereas on the right, we have the same plot, but for the iron top position, and the agreement is even better in the order of 6%, which seems to confirm that the new reference values are coherent with the experimental measurements. So to conclude, and to conclude the 2 talks, from Marco and myself, CERF provides the worldwide user community, and especially Eurados, with a well-characterized workplace radiation field, where Fluka simulation performed to provide new reference values that were documented in a peer-reviewed paper and benchmarked against the most recent experimental measurements. And as already said, the numerical values will be soon available on the new CERF website. So in case you have any question, you can contact Marco or myself at the following addresses. And And just to conclude, the same bibliography provided by Marco. Clearly, it's not an exhaustive list, but at least it resumes the papers I cited in this presentation. And I'd like to thank you for your attention.
Okay, thank you very much, Fabio. So I would like to repeat that you can write all questions you have in the question and answer, or even in the chat. I didn't see any specific question yet, but we will handle them all at the end. So we can go immediately then to the third and final presentation of today. This will be given by Robert Früschel, also from CERN, and he will talk about the CERN shielding benchmark facility. Robert?
Yes. Yeah. So good afternoon, everybody. Let me please present you today the CERN shielding benchmark facility, or CSBF. Since the CSBF is embedded in the shielding of the CHARM facility, I will start with a brief introduction to the CHARM facility. And then I will come to the motivation for the CSBF, the layout, the capabilities, the benchmark campaigns, and the exploitation modes. In this slide, you see an overview of the CERN Accelerator Complex. On the top, you see the LHC as a blue ellipse, but of course the protons for the LHC do not start in the LHC. So there is a whole injector complex to feed the LHC. And on the center bottom, you see the PS, which is the CERN proton synchrotron, and connected to the PS, visible on the very right, is the East experimental area, where the CHARM facility and the CSBF are located. Here you see a sketch of the Margaret Site with the CERN accelerator tunnels indicated in blue. The circle in the center indicates the CERN PS, and the CERN PS then feeds the East experimental area and then the CHARM facility that is located in that area. In this graph, you see a horizontal cut of the CHARM facility. So the beam would come from the top left, transverse the facility, and then hit the target in the center of the CHARM facility, producing the radiation fields inside the CHARM facility for the testing of electronic equipment. And the CSBF is located right above the target of the CHARM facility. Here you see a photo of the shielding structure of the CHARM facility. So the beam would come from the very far right and then traverse inside the shielding and hit the CHARM target right below the place where the shielding is the thickest, and which is also the place where the CSBF is located. And to give you an idea, the height of the shielding over the CHARM facility is 8 meters from the floor level of the east area. So the purpose of the CHARM facility is to study radiation effects on electronic components in the framework of the Radiation to Electronics project at CERN. And the CHARM facility receives primary protons from the PS with a beam momentum of 24 GeV/c with a maximum intensity of 5×10 to the 11 protons per pulse. Under normal operation, it's a slowly extracted beam of 350 milliseconds pulse length, and the maximum average beam intensity that can be reached in that facility is 6.6×10 to the 10 protons per second. The CSBF is meant for the characterization of different shielding materials and serves mainly deep shielding penetration studies. So one can expose passive detectors, so this could be activation samples or passive dosimeters for Monte Carlo simulation benchmarks. One can expose active detectors on the top of the shielding to a deep penetration neutron spectrum, and on the same location, one can also expose dosimeters attached to phantoms. And there's a dedicated location for attenuation length measurements for different shielding materials, where we have a lot of different shielding blocks to realize a lot of different shielding configurations. And this is complementary to the CERF facility, where we talk about shielding thicknesses of 40 or 80 centimeters. The CSBF, as said, is situated laterally above the CHARM target. It's a combined facility of the experimental area group, the R3 project, and the radiation protection group. And since 2016, we are running in an upgrade mode that allows for 3 principal modes of operation. I will come to those modes in the next slides. And until the start of the long shutdown 2, that is still ongoing, we had 3 years where per year we got 1 week of dedicated beam time for the facility. Otherwise, we can make parasitic use of the radiation field from the charm target during normal operation. And each Wednesday, there's a stop for several hours where we can exchange samples. And the facility is conceived in a way that we can fit within the time window of these stops for sample changements. And the design of the CSBF was based heavily on Fluka simulations, and all the measurements that we have done really confirm that Fluka is a very suitable tool for these kind of applications. And I would like to invite you to go to the webpage fluka.cern, where you can find the latest Fluka version that is now hosted at CERN and developed by the International Fluka Collaboration. I come to the first mode of exploitation. So you see on the left, you see a vertical cut through the shielding structure along the beam line, along the beam path. So the beam would come from the left, impinge on the target on the bottom, and then the CSBF is situated right above the target. And if you see on the right, you see the removable sample holder concrete block. That is a block with 3 empty slots where one can place samples, or also on the top of the block one can place samples. And on the left, you find this sample holder block inserted into the shielding facility. So one can place samples, expose them, and then take them out again. This is the first mode of exploitation. The second mode is available when this block is removed from the facility, and then the facility looks like this. So there's basically a gap in the facility, a duct, which means that up this duct, one has a collimated neutron beam that impinges on the shielding materials that are here indicated in orange. And these shielding materials can be selected from a wide range of shielding materials to select a certain configuration that is of interest to the measurement. And the third possibility is to remove the barred concrete blocks that are indicated in blue, while having the shielding, the holder block inserted. And this creates what we call CSBF platform. So that is a platform of 1.2 times 1.6 meters, where one can expose detectors or dosimeters to a deep penetration neutron spectrum. To give you an idea of this is the Fluka model of the facility when the CSBF platform is exposed. And now I come to some photos that characterize the facility. So here you see a radiation detector right above the CSBF. So approximately 7 meters below this white detector is the charm target where the beam from the PS is impinging. And one can remove the block that is situated below this white radiation monitor. These are photos of the removable sample holder concrete block when it is to be inserted, and the insertion is done with a remote controlled hook where one can lower the block and then electronically unlock the hook and then get the crane up again. And here you see the 3 slots also where one can pose samples for irradiation. This is when the holder block is inserted into the facility, and on the right you see then the final configuration when the block is really down. This is an example of when the shielding material is inserted in the shielding material test location. That is a big cast iron, big steel block. And this is another example where a concrete block is inserted into the shielding test location, and the radiation monitor is placed on top of it for measurements. And then we come to the CSBF platform. So this is one of the 2 blocks that has to be removed to expose the platform, that then looks like this. So there are stairs going down, and on the bottom of this these stairs you see the platform that is, as I said, 1.2 times 1.6 meters, and on the right you see a radiation monitor exposed at that location. Coming to the radiation fields, on the left you see the neutron fluence for newtons above 20 MeV, and on the platform you have approximately 100 newtons per square centimeter per second, with a full beam intensity. On the right you see the ambient dose equivalent rate, where on the platform you are a bit below 100 microsievert per hour, whereas in the lowest location for the holder block, one goes to the range of approximately 100 millisievert per hour. And these are the neutron spectra on the left for the 4 locations of the sample holder block. The first location you see in blue that has the least shielding, and then as you progressively go higher in the shielding, of course, the lower the spectrum gets, but also the shape changes. And then in the end, you're really in a deep shielding equilibrium spectrum. That is the same, that is confirmed then on the CSBF platform, where you see the spectra for the various locations. So also on the platform, one is really in this deep shielding equilibrium spectrum. This is a list of the available shielding blocks that we can insert into the material test location, and you see the different types of concretes, cast iron, steel, to realize different shielding configurations that are of interest. In terms of operational capabilities, we are heavily profiting from the IRAD and CHARM facilities that have been constructed in 2014. So we can get the maximum intensity of 5 × 10⁻¹1 per spill, but we can also go down to 3 × 10⁹ protons per pulse with a dedicated extraction for us. This can be fast or slow extracted, and then we can choose 3 different types of targets. So there's a copper target, an aluminum target, and then an aluminum target with holes to reduce the effective density of the target, which means that in the end, we can vary the beam intensity or the radiation intensity coming from the targets with 3 orders of magnitude. For the beam instrumentation, we have secondary emission chambers for the spill intensities, beam position monitors, and all this data is fully locked in the CERN machine database. For active measurements, there is also a pre-trigger signal that we can receive 100 milliseconds before the spill arrives. And on top of that, independently, we have the whole radiation monitoring system of the CHARM facility that provides an online supervision that also fully locked. And on this slide, you see the definition document. So all around and on the roof, we have the green monitors that are neutron monitors, and inside we have ionization chambers that can also be used to independently assess the beam intensity. For the benchmarks, I would like to show you one example. These are activation benchmarks that we have performed. Typically, we expose bismuth, aluminum, graphite, and indium samples at different heights in the block, different thicknesses of the concrete and iron in the material test locations for the copper target, and then we compute with Fluka specific production yields, and then we measure for the samples the specific activity, and taking into account the beam intensity profile, we compute back the production yields. And one of the benchmarks we have already published, and we have an extensive data set that we will publish in the next months, and the agreement is always within a factor of 2. You can see an example here. So as a function of the shielding thickness for different reaction channels, you see Fluka and measurements on the top and the ratio on the bottom. And this is the factor of 2 that I have spoken about. And the same is true for other, for aluminum and graphite samples. And this plot, this is at the 3rd slot of the sample holder block, is the cumulative contribution to the production yields as a function of the neutron energy on the x-axis, and this gives you an idea which energy ranges of the neutrons are assessed by these benchmarks. And typically we assess from several MeV until, let's say, 150, 200 MeV with this type of reaction channels. Then coming to the exploitation modes. So prior to LS2, we had 1 week of dedicated beam time. For the beam period after LS2, which means run 3, this still is under discussion, but most likely the CSBF will restart in 2022. We have until now spent the time characterizing the CSBF and validating the Fluka simulations. This is ongoing, and produced a lot of new experimental data for neutron spectrum measurements and Monte Carlo simulation benchmarks. Typically, this also involves several colleagues from Japan, from KK and other institutes, and there's a variety of different kind of measurements that we have performed in that facility. And in the end, you can also find the publication lists of the analysis that are already published. This brings me to the conclusion. So the CSBF is a facility for deep shielding penetration studies based on Fluka simulations It's a very flexible facility with several exploitation modes, and the configuration changes can be done quite quickly. It's well instrumented and extensively benchmarked, and this is done all in collaboration with our colleagues from Japan and of course from CERN. Here I give you an overview of the publications that are already out, and there are several in the pipeline still. This is of course work that one cannot do alone, so there are a lot of people and groups at CERN that have contributed to this. So the experimental area group, RTE, the operation teams, integration, gamma transport group, gamma spectrometer laboratory, and the cryogenics group. And I would end with a picture of how the CSBF looks today, and there you see all the different shielding materials that are available for tests. Thank you.
Okay, thank you, Robert. We finished the 3 presentations. I see there are some questions. I also understood that Marco's connections problems hopefully are solved, so he can take over for the questions. I just want to answer first because there are some questions from some people asking about if the slides will be available. Well, we have from the 3 presenters, so actually I would like to thank a lot for their contribution, of course, because it was very good. So from the 3 presenters, we had we could record the presentations. So basically, the whole presentation that we just followed is recorded, and we plan to put this on the Eurodose website. Actually, but this can take a few more weeks because we are restructuring the website, so it can take a little bit longer before all information on the webinars is really available on the Eurodose website. So we will look for an intermediate solution, and probably we will be able to send a link with the recording tomorrow to all participants. So if all goes well, you will receive tomorrow an email with the link to the recording, and you can just watch again if you really liked it, the presentations, and you can also get the information from the slides. But in a few weeks, also the slides will be available on the Eurodose website. And by this, I give the word back to Marco to handle the questions.
Thanks, thanks, Philip. And I hope my connection works better than before. So we have several questions. The first one is from Werner Rome, who is asking to Fabio, how do your Fluka calculation compare with those presented by Bral and Al, and also using GEM4?
Thank you, Werner, for the question. So there are a few things to mention about this kind of intercomparison that we did not do so far, but would be interesting maybe to perform within the working group 11. So the first thing is that we use different geometries, mine and the one used by Thomas in his article, as well as different chemical composition. I just checked, and the two are not really the same. And as I mentioned before, those are parameters that can really affect such kind of comparison. So one should maybe plan it in a proper way in order to be able to compare the different groups. Anyway, I've seen that Thomas, he compared the results of the GEM4 simulation with the former reference spectra. So the old one done with Fluka 92. That's why it would be interesting to repeat such kind of comparison with the most recent one. There was a comparison in the article for what concerned the ambient dose equivalent. And in that case, the new Fluka simulations underestimate by, let's say, 10 to 15% the results from GEM4. So this seems to be quite a systematic underestimation, and can be due to the aspects I just mentioned before.
Okay, thanks a lot, Fabio. The second question was from Denek Vikidal, if I pronounce correctly the name, about the availability of the presentation, but Philip has already answered. Then there is a question from myself to Fabio. And well, Fabio, when you presented the comparison in between the new Fluka calculation. And the Linus, how was calibrated the Linus?
So the Linus was calibrated with the standard Americium beryllium source to guarantee the traceability of the detector. So it's, let's say, a sort of independent calibration from the CERF.
Okay, thanks a lot, Fabio. Then we have another question from Brian Michael Hayes, who asking a comparison between the CERF spectra and the one at commercial altitude of airlines. So maybe Marco, you are the correct person to answer that.
But okay, there are some publications which I think are listed on our website. We are trying to update the website with all the publication of work performed linked to CERF. They are rather similar. I cannot tell you how close they are, but I mean the CERF spectrum is rather similar to the neutron spectrum that you find at altitude. For instance, I remember we had Frantic Esperni was actually measuring on board planes with the bubble detectors, were actually calibrating the bubble detectors in the CERF field and use the calibration factor obtained at CERF to measure on planes. So lots of people actually, you can actually calibrate in what is called the workplace, which is rather similar to the one we have in on board planes.
Okay, thanks, Marco. Thanks a lot. Another question is from Robert Ice about the cost of the beam time. So maybe Marco, you can.
Zero. I mean, the CERN does not charge for beam time. I think once I made the exercise to see how much would it cost, it's going to be a fortune, of course. No. I mean, what we do, we typically, I think it's the same for Robert's facility. But what we do, we ask for beam time to the SPS physics coordinator, typically in the beginning of the year, and well, the point, and I mean, exploiting CERF is just on our own shoulder, our own resources. So we cannot run for 2 months. So we have to be for 1 or 2 shifts or 5-6 days. When we have the beam time, I have a mailing list where I distribute the call for beam time. So people can ask for beam time. They will to provide them, what they want to measure. I mean, which field, how many shifts they want. And normally we try to accommodate all of the requests, but apart from, so of course they're not providing any support for travel or accommodation. That's the charge of the user, but there's no cost for the, for measuring. And I think the same with your facility, Robert, no?
Yes.
Okay. Okay, thanks. Another question is from Herald Dombrowski about the gamma spectrometry at CSBF. So
the samples were taken out of the CSBF and typically sent to the CERN gamma spectrometry laboratory, and there we have high purity germanium detectors.
Okay. Then we have a question from Rick Tanner, who is interested in the calculation of the new SRU quantity itself. He was told by one of the authors that quantity HP is receptor present, which would require a voxel phantom to be included in the model. So maybe Fabio, you can.
Yeah, in our case, this was not included. The voxel phantom was the scoring of the track length density. So let's say the particles fluence spectrum, and then we fold it with the coefficients. So let's say it was quite a simplified approach.
Okay. So we have another question again from Tanik Wikidal. That is, what ratio are compared between old and new Fluka calculation on slide 51? So to Fabio.
Yeah, that's ambient dose equivalent, so H star 10.
So is the ratio in between the H star 10 compared with the new and old?
Yes.
Okay, that was the last question. I don't know if I have a look also in the chat. But I cannot see any other question even in the chat. So it's exactly 5 p.m. So we are in perfect time, and I would say that if there is no other question, I guess we can close here this webinar. Thanks again the 3 speakers, but I also want to thank all the audience that was really important in this number. It's not an exact figure on that. Sorry, I have some noise in my microphone.
Yeah.
I hope you also had.
Yes.
So, unfortunately, maybe my connection says that it's really time to close the webinar here. So, thanks again to everyone, speakers, and also audience.
Thank you.
Hope to see you at the next annual meeting in a few days.
Goodbye.
Good evening, everyone.
Thank you. Bye.
Bye-bye.